In a closed system, energy changes are due to heat and work, with the total energy change equating to the change in internal energy. This principle is fundamental in analyzing thermodynamic systems. Moving boundary work involves the expansion and compression of gases, with work done as the boundary moves. This concept is essential for understanding processes in piston-cylinder devices. The boundary work done during a process is represented by the area under the process curve on a PV diagram. This visualization helps in understanding the work involved in thermodynamic processes. Different thermodynamic processes include constant volume, constant pressure, constant temperature, and adiabatic processes. Each has unique characteristics and applications in engineering. In a constant volume process, no work is done as the boundary does not move. This process is characterized by a zero area under the PV curve, indicating no boundary work. The non-flow energy equation for a constant volume process highlights that energy changes are due to heat transfer, not work. This equation is crucial for analyzing energy changes in such processes. Let's explore how to calculate the change in internal energy when 1 kilogram of air is heated at constant volume. Starting with a pressure of 100,000 pascals and a temperature of 300 K, we heat the air until its pressure reaches 250,000 pascals. Using the specific heat capacity at constant volume, we can determine the change in internal energy. In a constant pressure process, work is represented by the area under the pressure-volume curve. As we heat the system from state 1 to state 2, the pressure remains constant, and the work done is the product of pressure and the change in volume. The non-flow energy equation in a constant pressure process shows the relationship between internal energy change, heat transfer, and work done. As we heat the system, the equation helps us understand how energy is distributed between these components. In a constant temperature process, the ideal gas law tells us that if temperature remains constant, the product of pressure and volume is constant. This relationship helps us calculate work done during heating, represented by the area under the curve. Continuing with the constant temperature process, we use the ideal gas law to express work done as a function of volume change. This equation helps us understand how energy is transferred during heating when temperature is constant. An adiabatic process is characterized by no heat transfer to or from the control volume. In this process, the work done is equal to the change in internal energy, as the system is insulated from external heat exchange. In an adiabatic process, the relationship between pressure and volume follows the equation PV(gamma equals constant, where gamma is the isentropic index. This equation helps us calculate work done without heat transfer. Further exploring the adiabatic process, we use the equation for work done involving the isentropic index. This formula allows us to calculate work done based on pressure and volume changes without heat exchange. Many real processes follow the polytropic process law, where the product of pressure and volume raised to a power is constant. These processes help us understand energy transfer in systems where heat exchange occurs. In polytropic processes, the non-flow energy equation provides insights into how energy is distributed between internal energy change, work done, and heat transfer. This equation is crucial for understanding real-world energy systems.